If you're enjoying Why This Universe, there's another University of Chicago podcast network show that you should check out, and it's called Capital Isn't. Capital Isn't uses the latest economic thinking to zero in on the ways that capitalism is, and more often isn't, working today. Join Vanity Fair contributing editor Bethany McLean and distinguished professor of economics Luigi Zingales as they explain how capitalism can go wrong, and what we can do about it. Listen to Capital Isn't, part of the University of Chicago podcast network. So today we are talking about something so deep and so profound that it's basically the poster child for beauty in physics. And so we're going to be talking about Noether's theorem. This theorem is named after the mathematician Emmy Nother, and yes, you heard that right, she wasn't even a physicist. So how does a theorem about pure math, discovered by a mathematician, end up becoming so central to physics? Stick around to find out. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So to talk about Noether's theorem, we have to start by talking about symmetry. Symmetry is probably a familiar concept for you already. Something like flipping a square around and it looking the same, or rotating a circle to get the same circle. These are all examples of symmetries. But in the world of physics and math, symmetries have a much more general definition.
So those things are definitely all symmetries, but we can kind of generalize this idea and just say something has a symmetry if there's some operation you can do to it that leaves it unchanged. So if I take a perfect square and I rotate it by any integer number of 90 degrees around its center, you still have exactly the same square. So the operation that I'm talking about here is that rotation by 90 or 180 or 270 degrees or whatever. And that leaves you with the same thing you started with. And that means the square is symmetric. It has a symmetry.
So geometric symmetries, like with the square, might be some of the most obvious examples. But there are tons of different kinds of symmetries in math that are way more abstract.
Like if you take all of the integers from minus infinity to infinity, and you take that whole set of numbers and add, 7 to all of them, you still have the same set of numbers. 7 turned into 14 and minus 3 turned into 4. But in the end, you have exactly the same set of integers that you started with. So we like to say that the set of integers has a symmetry, which is under the operation of addition.
Okay, so what does this all have to do with physics? Well, imagine that instead of adding 7 to every single integer, you instantaneously move everything in the universe 7 inches to the left. It turns out that doing that would not change the physics of the universe at all. So that operation of moving everything 7 inches to the left actually reveals a symmetry inherent to the universe. And so physicists are very interested in thinking about symmetric operations like this one. The thing is, though, before Emmy Noether, it wasn't ever clear why the universe had the symmetries that it does.
So what Emmy Noether did is take this concept of symmetry and apply it or embed it deeply into the laws of physics. So she has these two theorems, and we're really going to focus mostly on the first one here. Basically, what she says is that for every symmetry that's present within any laws of a physical theory, there's always a corresponding conservation law. Symmetries and conservation laws are really the same thing, according to Emmy Noether and her first theorem.
So let's go back to that symmetry where we moved everything 7 inches to the left and saw that nothing changed.
That's because the laws of physics have built into them a symmetry that respects translations in space. And this symmetry pertaining to space is related through Noether's theorem to the conservation of momentum. In other words, in any universe where the laws of physics respected the symmetry of space, momentum will be conserved, and vice versa.
So just in case you don't know, here's what momentum conservation is. The quantity momentum is related to an object's mass and the speed that it's traveling at. So a heavier object or an object traveling faster has a higher momentum. So if you have a few objects and say at one moment you stop the clock and add up all of their momenta, then you let the clock go on and the objects can move around, maybe they collide with each other, exchange some energy, and then later you stop the clock again and add up all their momenta again. You'll find that no matter how much time has passed, the total momenta of the system will not change. The number that you got when you first stopped the clock will be the same as the one later. This kind of conservation law is taken for granted in, say, an introductory mechanics class. But Nother shows us that there's a deeper reason behind this kind of conservation.
And it's not just momentum in space, but there are lots of these relationships that Noether's theorem connects. So for example, there's a symmetry in the laws of physics that says that if you move things forward or backward in time, everything stays the same. So this is a translation in time. And that maps on to the conservation of energy through Noether's theorem. Similarly, if you rotate the whole universe by some common angle or something, the physics is all the same. So this is a rotational invariance, and Noether's theorem relates that to the conservation of angular momentum. Later in this podcast, we'll talk about gauge symmetries or symmetries under gauge transformations, and it turns out those are connected to the conservation of electric charge.
So quick question. We mentioned that the conservation of energy is related by Noether's theorem to a symmetry in translation in time. We've done, though, a previous episode talking about how time does move in one direction and that there is some asymmetry in time. So how does that track?
So it is true that just very, very gently, the direction moving forward in time is not the same as the direction moving backwards in time. But if I took everything in the universe now and moved it into the future and then let it move again, everything would happen the same way. It doesn't matter if you started at time 0 or time 10 or time 1 billion. The way that time advances forward and the laws of physics that play out are the same no matter what time they're playing out in. In other words, the laws of physics don't change as time advances.
In other words, translations in time are symmetric, for example, changing the clock to be 10 minutes ahead, but time reversal is not necessarily symmetric, so like running the clock backwards and seeing everything in the universe move backwards in time. So check out our Why Does Time Move in One Direction episode to hear more about that.
So it's important to recognize that when we talk about these symmetries, we're not talking about symmetries built into the objects in space. So if I had some like irregularly shaped rock or something, it would spin in some irregular way, not in some sort of not in the same way that a perfectly symmetric sphere would rotate. When we use Noether's theorem, we're not talking about the symmetries of the objects. We're talking about the symmetries built into the laws of physics that tell those objects how to move. So even though an irregular rock isn't itself symmetric, the laws of physics that tell it how to move are, and for that reason, it respects things like the conservation of angular momentum and energy.
So that's the rundown of what Noether's theorem tells us, and there's really no way to overstate how much her discovery changed physics forever.
Before Emmy Noether in her work, there was really no deep understanding for why laws of physics had these conservation laws built into them. They just kind of noticed through trial and error that these quantities always seem to stay the same, like especially energy conservation. When Isaac Newton worked out his system of physics, he didn't really talk about the concept of energy, and he didn't seem to notice that anything like that was conserved. A few decades later, the French philosopher and mathematician Émile du Châtelet, I apologize to any French speakers for my pronunciation, he pointed out that the energy conservation follows directly from the structure of Newton's theory, but the deep connection with symmetry was totally missed to the scientists of that day. After Emmy Noether proved her famous theorems, though, it was understood for the first time that these conservation laws were really coming from the deep symmetries that were built into the structure of space and time. So let's take a step back from the physics for a minute and talk a little bit about Emmy Noether in her life. It's a pretty interesting story. So she was born in 1882 in Erlangen, Germany. And in some ways, I would say she was a pretty privileged individual. Her father was a math professor at the University of Erlangen, and she had every kind of educational advantage that somebody could have in that time or place. But even with those kinds of privileges, there were huge barriers for any woman who wanted to take part in mathematics or academia. She went to the kind of highest level schools that girls were allowed to go to, and she passed all the qualifying exams that would allow her to do things like teach English or French. But they weren't allowed to enroll in universities. The best they could do would be to get permission to like sit in on lectures, and she did that. And she just couldn't really become a real mathematics student given the rules at the time. In 1903, a nearby university in Göttingen kind of relaxed those rules, and she enrolled there. And then after a couple more years, the university in her home city of Erlangen relaxed those rules, and she started to be able to take classes there for the first time. It's hard to overstate how big the names of mathematicians in this part of Germany was at this time. We're talking about people like Karl Schwarzschild, who was there, the guy who found the solution up to relativity that we associate with black holes. Hermann Minkowski was there. He did some really important early work on special relativity. Felix Klein, who we talked about in our episode on extra dimensions. David Hilbert, who was probably the most famous mathematician in the world at the time. All these people walked the hallways of this university. So, she had a lot of advantages there. So Emmy Noether completed her dissertation in 1907, making her only the second woman to ever earn a PhD in math anywhere in Europe. So definitely a pioneer. Her thesis wasn't on a particularly exciting topic. It wasn't, I would say, like her most creative or abstract work. That would come later in her life. But I just think she wasn't given the opportunity to work on the choice topics. As a woman, she was always given kind of the least attractive ideas of projects and just was kind of disadvantaged at every turn. And then after she got her PhD, she spent the next 8 years without any pay doing research and teaching at this mathematical institute in Erlangen. She distinguished herself, but still didn't get anything for it. So she joined the German Mathematical Society and was the first woman ever to lecture at their annual meeting. Her research had become more abstract and more creative and more influential. And yet she just couldn't land a real academic position, all because of her gender. She was always trying to get a real academic position, but she just kept being pushed back. In 1915, she applied for a position that was kind of like the equivalent of an adjunct professorship at Göttingen. And one letter, now this is a letter in support of her application. That's important to recognize. But this letter said, quote, "I have had up to now uniformly unsatisfactory experiences with female students, and I hold that the female brain is unsuited to mathematical production. Miss Nother seems to be a rare exception." Mm-hmm. So this is what somebody says if they think she should get the job. Can you imagine what the opponents were saying in 1915?
I mean, this isn't as outdated as you think. I've had a high school math teacher of mine tell my parents that I have a male brain.
Oh, it's so obnoxious. I mean, you were in high school not very long ago, Shalma. There's really no excuse for that teacher of yours. All right. So Noether's appointments were always voted down. Despite this, though, she had some pretty powerful allies, and it gave her some opportunity to participate in academia, even if through kind of non-traditional means. So David Hilbert was a big proponent of hers. Again, maybe the most famous mathematician in the world at the time. And he would sign up to teach a class knowing that he would turn it over to Nother. He would have the power to create a class and, basically set up the curriculum. And then Emmy Noether would show up and teach the whole class. And everybody knew this. And she was apparently just brilliant. And everyone was happy with that, even though the rule said it couldn't be done. But eventually this stuff started to relax. And after World War I, a few women were allowed to teach in the German universities. And in 1919, Noether was finally granted a position, still with no pay. I can't believe that, but still no pay. And this was just after her publication of her most famous work, her two theorems. I guess you have to do, you have to publish one of the greatest proofs in the history of 20th century mathematics to get a job if you're a woman at this time. But she met that bar, that very, very high bar. And, the rest is history.
It's just another example of how much higher the bar is to prove yourself when you don't look like the people who are traditionally in your field.
Yeah, if I had to, do something of that caliber before I got my job, I would definitely not have made that bar. Yeah.
And even with her brilliance, it took being able to survive for years without pay and the help of male allies to help her get where she did.
I mean, just think about how many women there were at that time who might have been just as potentially brilliant who didn't have the luxury or the privilege of being able to do math all day without any pay for years and years and years.
And think about the people today who are facing marginalization in the field of physics. Think of people of color, women of color, people who might not have mentors looking out for their success, or who might be dealing with abusive situations, or maybe even a lack of financial support. There are lots of ways that physics is still gatekept from brilliant people who could potentially make huge impacts if they were given the tools to. I think Nother's story is an important peek into what it really takes for someone from a marginalized identity to make it in a field that doesn't ordinarily accept them. But now that we've heard this story, let's go back to the physics. And let's see how Noether's theorem has become so ingrained in even our most modern theories of particle physics.
So, as we've been saying, Noether's theorem relates conservation laws to symmetries. And most of the symmetries we've been talking about so far are external symmetries. They're symmetries that have to do with space or time. These are things you can kind of picture out in the world somewhere. But Noether's theorem also relates conservation laws with internal symmetries that are built into the structure of physical theories. The most important of these internal symmetries are known as gauge symmetries.
So, for example, the equations that describe electricity and magnetism, known as Maxwell's equations, these have a gauge symmetry. Basically, this gauge symmetry tells you that there's some freedom in how you can mathematically describe electric and magnetic fields. Like, I can write down two different equations, and these equations could both describe the same exact physical field. So we call each different way of writing the field a gauge, and this ability to use different gauges to talk about the same exact physics is called gauge symmetry. So it's quite abstract since it's not necessarily a symmetry you can go and see for yourself in nature, but it's there nonetheless, and because of Noether's theorem, it's actually pretty important.
So with this in mind, let's talk about the conservation of electric charge. So this is an incredibly experimentally validated conservation law. We've never seen the net electric charge change in any interaction. And probably the single most powerful test we have of this has to do with the fact that electrons don't seem to decay. Now, in general in physics, any particle with mass that can decay, that there's no law explicitly prohibiting that decay, it will break up and turn into lighter particles. This is just kind of the same reason why if you take boulders and put them on mountains, they tend to find their way in the valleys. It's just they want to get to this lower energy state. But in the case of the electron, this is the lightest particle with any electric charge. And that conservation of electric charge makes it impossible for that electron to break up or become lighter particles. Experimentally, we know that the electron lives for at least 10 to the 29 years based on experiments like the Borexino neutrino experiment in Italy, which is an incredibly long lifetime. And the fact is probably the electron just lives forever because the conservation of electric charge is a perfect symmetry of the laws of physics. All right, so this raises the question of where does this idea of the conservation of electric charge come from? Like, why is this so perfectly manifest in the laws of physics? The equations that describe classical electricity and magnetism, the Maxwell's equations, were actually designed to conserve charge. Like they put in this thing by hand called the displacement current just to make sure that charge would be conserved. So you shouldn't think of these equations as offering an explanation for why charge was conserved. They were just kind of reverse engineered to make sure it would be. Through Noether's theorem, we get a much deeper understanding of where this charge conservation comes from. And this gauge symmetry, this peculiar feature built into the Maxwell's equations, is exactly mappable onto the conservation of electric charge. And it was Emmy Noether's theorem that allowed us to understand this for the first time.
So this sort of gauge symmetry is at the heart of particle physics. The gauge symmetry that we were just describing that relates to the conservation of electric charge is the gauge symmetry of the electromagnetic field. But there are similar types of gauge symmetries at the core of quantum electrodynamics, for example, the quantum version of electricity and magnetism. This is sometimes called QED. And there are other similar symmetries in the Standard Model of particle physics itself.
It turns out that when you construct particle physics theories that have these sorts of gauge symmetries built into them, they have a certain kind of mathematical self-consistency that's guaranteed. They have this feature that we call renormalizability. That means all the sort of physical quantities that you want to be able to predict with the theory will be finite. They won't explode and go off to infinity in a kind of nonsensy sort of way. By working with theories that are gauge symmetric, we can avoid all these mathematical catastrophes that other theories might have.
And apart from being good theories to work with, these symmetries also imply a handful of very important conservation laws throughout particle physics, thanks to Nother's theorem. For example, particles called quarks carry this special property that physicists call color. So it's not literally what color they are, but for some reason that's just the language to describe them. So quarks can be called red or blue or green, and it turns out that by Noether's theorem, and by the gauge symmetry of the Standard Model, color is actually a conserved quantity. So if in some interaction between particles, one particle gains a blue quark, then another particle must have lost a blue quark, and so on.
And also things like the total amount of protons and neutrons minus the total number of electrons in their kind of particle, all that's conserved as well, all built into the gauge theory structure of the Standard Model.
This whole idea of symmetries related to conservation laws, it's really been, a core important thing in building the Standard Model of particle physics, like our best current model of how all of the fundamental particles behave.
Absolutely. And furthermore, it's such a central idea and concept in contemporary particle physics that it's hard to even imagine a particle physics theory that anyone would propose that doesn't have gauge symmetry built into it in a deep and powerful way.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.